Deep inside the cowling of an aircraft, pistons slam back and forth, containing thousands of controlled explosions every single minute. The cylinders endure immense pressure, extreme friction, and raw mechanical violence. An airplane engine utilizes the same four-stroke internal combustion cycle as a standard automobile, yet the demands of flight require a distinct and highly specialized architecture. While a car operates largely at sea level, an aviation power plant must survive rapid, severe drops in air density and freezing ambient temperatures. Most importantly, it must function completely isolated from an external electrical grid. To understand how it survives these extremes, we are going to build a four-cylinder horizontally opposed engine from scratch. We will construct its four main pillars: mechanical timing, ignition, fuel induction, and thermal management. This creates an interdependent ecosystem where a failure in any one pillar cascades instantly to the others. We begin with the bare foundation of the horizontally opposed reciprocating engine, a central, rotating crankshaft surrounded by cylinders. The combustion process here is governed by the Otto cycle, developed by German engineer Nikolaus Otto. It consists of four distinct strokes of the piston: intake, compression, power, and exhaust. Because the fuel-air mixture is only ignited during the third step, the power stroke, the engine generates power on only one out of every four strokes. This means the engine requires 2 full revolutions of the crankshaft to produce a single power event per cylinder. This creates an immediate mechanical timing problem. At a typical cruise speed of 2,400 revolutions per minute, the intake and exhaust valves must open and close exactly 20 times every single second. This diagram shows the exact valve opening and closing durations across a full 360-degree crankshaft rotation. At 20 cycles a second, opening a valve at the exact mathematical top or bottom of the piston stroke physically chokes the engine. Engineers solve this by utilizing valve lead and valve lag. Valve lead opens the intake valve slightly before the piston reaches the very top of its stroke, allowing the cylinder to catch the expanding gases as early as possible. Valve lag then keeps that intake valve open slightly after the piston passes the bottom of its stroke. This utilizes the physical momentum of the incoming, fast-moving air mass to cram more volume into the cylinder. This precise, overlapping choreography maximizes the intake of the fuel-air mixture, allowing the engine to breathe and sustain power at high rotational speeds. Why does an aircraft engine deliberately disconnect its spark plugs from the main battery system during flight? Safety requires a reliability mandate. The engine uses internal, mechanically driven generators called magnetos. As the engine turns, the magnetos use magnetic induction to generate high-tension current, operating entirely independent of the aircraft's electrical grid. Aircraft utilize dual ignition, where 2 separate magnetos fire 2 independent spark plugs inside every cylinder. This provides life-saving redundancy while creating dual flame fronts for a faster, more complete combustion of the fuel. However, this creates a physics problem during startup. A magneto requires 100 to 200 RPM to generate a spark, but a standard battery-powered starter motor only turns the engine at roughly 60 RPM. Furthermore, firing a spark before the piston reaches the top, a necessity at high speeds, causes kickback at low RPMs. This early explosion forces the piston backward, potentially destroying the engine's internal linkages. This animation illustrates the mechanical solution to both problems: the impulse coupling. It is a specialized hub on the magneto shaft containing a coiled internal spring and mechanical catchweights. As the starter motor turns the engine, the catchweights hold the magneto shaft stationary. The engine's rotation winds the coiled spring tighter and tighter, storing the rotational energy. At the precise moment the piston reaches the top of its stroke, the catch releases. The spring snaps, spinning the magnet incredibly fast to generate high voltage while simultaneously delaying the ignition timing to push the piston safely downward. The impulse coupling bridges the physics gap, using the slow turn of a starter motor to jolt a dead engine to life and achieve absolute electrical independence the moment it takes to the air. For combustion to occur, the engine requires a precise chemical balance.
The stoichiometric ideal is approximately 1 part fuel to 12 parts air by weight. This diagram shows the mechanical mixer responsible for that ratio, the float-type carburetor. As air flows into the intake, it hits a narrowed section called the Venturi throat. Restricting the airflow accelerates it, causing a sharp drop in static pressure. This low-pressure zone acts as a vacuum, drawing fuel out of the adjacent float chamber and through the main metering jet. This vaporizes the liquid into the airstream in direct proportion to the airflow velocity. While this system is effective at sea level, air density drops as an aircraft climbs. The Venturi throat continues to draw the same physical volume of air, but that volume now contains far fewer oxygen molecules. The Venturi pulls the exact same weight of fuel into this lighter mass of air, creating a dangerously rich mixture that wastes fuel and fouls the spark plugs with unburned carbon. The pilot corrects this using the mixture control. By manually adjusting a needle valve inside the carburetor, the pilot restricts the fuel flow to match the thinning oxygen at high altitudes. But the Venturi introduces a secondary hazard, carburetor ice. The sharp pressure drop in the throat, combined with the heat absorbed by evaporating fuel, turns the carburetor into a functioning refrigerator. As seen in this visualization of the internal passages, ice crystals accumulate aggressively on the throttle butterfly valve and the Venturi walls. This freezing action can choke the engine of air even on a 70-degree day if relative humidity is high. To melt the blockage, the pilot applies carburetor heat. This routes unfiltered, hot air from around the exhaust manifold directly into the intake, instantly raising the temperature and clearing the ice. Because an internal combustion engine is blind to atmospheric changes, the pilot must act as the engine's external brain, constantly adjusting controls to maintain stoichiometric and thermal balance. Thermal balance relies on a dual cooling system. Externally, cool air flows over the metallic fins of the cylinder heads. Internally, oil circulates to absorb friction heat and seal the moving pistons. This system is pushed to its limit during takeoff and steep climbs. The engine generates maximum heat at full power, while the aircraft's low airspeed provides minimum cooling airflow. When these thermal limits are breached, the smooth burning of the fuel-air charge breaks down, leading to catastrophic abnormal combustion. High pressures and temperatures trigger detonation. The unburned fuel-air mixture spontaneously and instantaneously explodes, sending shock waves that hammer the pistons and can shatter valves. Alternatively, a glowing carbon deposit on the cylinder wall can act as a localized hotspot. This causes pre-ignition, firing the mixture early and independent of the spark plug, while the piston is still traveling upward. Managing cowl flaps, monitoring the airspeed, and fuel enrichment directly prevents the engine from exceeding its thermal limits and tearing itself apart from the inside out. When we pull back and view the fully assembled power plant at cruise power, we see the ecosystem working in unison. The valves breathe, the magnetos spark, the Venturi mixes, and the oil cools. The controls in the cockpit carry direct physical context. The throttle dictates the air mass, the mixture knob commands the stoichiometry, and the ignition switch tests the independent magnetos. The pre-flight run-up serves as a systematic diagnostic interrogation of physics. By testing the magnetos, fuel flow, and oil pressure, the pilot confirms the ecosystem is stable before the aircraft leaves the ground. By mastering these first principles, by knowing exactly what happens behind the firewall, a pilot stops merely operating an airplane and begins to truly command it.